is Andrii Rublov. I'm a software developer at JetBrains, and I'm working at the Rider development team. During today's talk, I want to perform a deep dive into the hot reload functionality that we made in Rider, about the functionality in general and about the Blazor WebAssembly specifics in particular. In addition, I want to show you the way how we actually implemented it in Rider. So a little bit about me. At JetBrains, I'm involved in the support and improvement of the Blazor app execution infrastructure, including debugging and hot reload. Also in the anti-framework core tooling, NuGet package management, and some specific run configurations. In addition, among other projects, I am the author of anti-framework core and MonoGame plugins for Rider. By following the link provided on the QR code, you can reach me at any time via different social networks. So let's start from the very beginning. Let's understand what hot reload is and why actually we need it. The idea of hot reload sounds quite simple. You want to change code and see the changes immediately without restarting, without rebuilding, and nowadays is quite a common functionality in various web front-end frameworks. But it's not a new approach to .NET either. It has been used for different types of applications for quite a long time. Let's consider a typical approach to application development. A developer starts an application, validates its behavior in some way, then stops it, changes its logic, builds, and starts it again, and so on from time to time. Even with incremental compilation, such a cycle of work with code takes considerable time, especially if you need to make small changes and immediately validate the result visually. And this is quite a common task for programs that include UI development. For example, mobile applications, desktop applications, as well as web frontend. There are more rare cases, for example, when a program that you need to run should be firstly deployed to a device, for example, and not only for a simple device, but for maybe for industrial machine or something like that, and or the chip on a portable device, and then you need to do it again and again, and it takes some time. Now let's change it and think about how it could be, how this feedback loop could be done on using the hot reload mechanism. Basically, instead of stopping a program each time, we now continuously add changes and immediately see the result. For large, long, and complex changes, it's not very useful because it's hard to apply large changes at once. But to see how color of the button changes and how margins or paddings on different UI elements are changing and how they affect the look of the UI, it's very important. And this is a solution close to ideal because you don't need to do all this stuff if stopping and running again. And this approach greatly speeds up UI development and saves prototyping time when you just want to look at something new and prototype something, and you don't want to have to deal with all these restarts again and again. Now that we talked through the concept, let's take a bird's eye view of the state of implementation of hot reload infrastructure in .NET in general, without being tied to a specific framework. Currently, there are about 5 different implementations of hot reload functionality in .NET, depending on the platform, its capabilities, and user needs. The classic and most working approach is implemented in Core CLR runtime. It covers not only the console applications, but also ASP.NET Core and some other rare UI frameworks. Its implementation varies depending on whether the application is run in debug mode or not, as the change delivery mechanism in such cases is different. There is also a hot reload for XAML markup for different platforms. This is beyond the scope of today's talk, as it's very specific to the MAUI and other frameworks, and also the XAML hot reload for VPF and UEP are not currently implemented in Rider, but they will be in some future. Finally, the Blazor Wasm hot reload is our hero today. It actually combines two types of hot reload at once, but more on that later. Now let's take a closer look at each of these three remaining implementations. Let's start with the core CLR without a debugger. To say to runtime, hey, replace this CLI CL instructions with this, you must first understand where the changes have occurred. In modern.NET, the task of incremental code changes is handled well by the Roslyn compiler infrastructure. It has a mechanism that is expressed in the workspace abstraction. It allows you to create a certain environment around some set of C# files. It could be an MS build project or just a folder. It depends on different implementations that you use. And then calculates the changes that we need based on the changes in the source code. The workspace storage itself and the calculation of changes in the Rider implementation is done in a separate process called Roslyn Worker. Once we have a set of changes computed through Roslyn, we can start applying them. It happens through named pipes mechanism, the receiver for which is launched together with the user's application, called actually .NET Delta Applier. Noteworthy is the way in which the required infrastructure gets into the application domain. The mechanism is called startup hooks. With this, Rider injects the .NET Delta Applier, a library that has direct access to the runtime and can apply changes coming in via the named pipe. We'll come back to this beautiful and useful mechanism for embedding into .NET application later. In the slide, you can roughly see a simplified diagram of how such a pipeline for delivering changes to the runtime works. Let's consider a similar CLR scenario, but with the debugger added to it. In general, the approach of calculating changes for the subsequent application remains actually unchanged. So let's go straight to the application of the changes to runtime. The debugger worker involved in this scenario in a sidecar process of the main user application, and it's starting together with the application, and it implements the logic of working with the particular debugger API depending on the platform, on the runtime type, and other things. From a Rider front-end perspective, debugger worker is kind of a facet that has almost direct access to the runtime. It is mainly used for debugging, but in case of hot reload, it also used as a change delivery mechanism, particularly through the COM interface. On the slide, you can notice the annotated diagram where debugger worker actually replaces the named pipe from this previous slide. Now it's worth pausing for a moment to look at what the changes applied to runtime consist of. First and foremost, of course, are changes to the intermediate language code or the specific methods themselves. Also, on most hot reload platforms, if a currently executable method is affected, its current execution will be completed with the old code, and all subsequent runs, next runs actually, future runs, will be executed with updated code. In addition to the intermediate language code, the build metadata is also changed. Debugging symbols are also changed. This is necessary so that during debugging, breakpoints should point to the correct position in the code, and for example, current execution context should correctly calculate values, variables, watches, and so on. And finally, the list of updated types. This information is needed by the runtime to limit the pool of affected types and speed up the hot reload itself. Fortunately for us, IDE developers, all the necessary components stated here are provided by Roslyn from the modified workspace. Although in theory, hot reload sounds like a near ideal solution, it's actually not, because of the complexity of applying some changes to a running runtime, and they may not be available. Such changes are called root changes, and here is the list of a few important constraints in a form of changes that cannot be applied. For example, adding modified dynamic objects, deleting types, modifying interfaces, making abstract methods non-abstract, adding abstract virtual or override methods, modifying the type parameter, base type, delegate type, add destructor for an existing type. You can see the full constantly updated list of by the following QR code. This and other links will be also available at the end of the presentation. If a change is considered root, Wasm will return diagnostics about what went wrong at the time the change was occurred. Both .NET Watch and Rider support displaying such diagnostics before applying them. And Rider also usually displays the problematic code in the editor. Sometimes, such as in the case of Blazor applications, the pre-applied diagnostics don't always catch potential problems. This leads to runtime refusing to apply similarly, valid changes, and returning an error. This is due to specifics of the Blazor runtime, which we'll be discussing in the next chapter. With the basic features and functionality of hot reloading in .NET sorted out, let's look at what the additional challenges are in supporting hot reload for Blazor Wasm applications. It should be understood that each open tab with Blazor Wasm application is a separate runtime. Accordingly, having a common code base with the server, both the server and all running clients should receive changes more or less synchronously, or at least in some predictable order. Unlike the Asmech core server that hosts our client application, the Blazor Wasm client itself runs on a specially built mscripten mono runtime. Mscripten, for folks who don't know about it, is a toolkit and a compiler that allows you to turn programs written in low-level languages such as C, C++, and other ones into JavaScript and WebAssembly modules. Mono runtime was much easier to port to a browser than core CLRs. That's because which at the time of Blazor creation was not yet ready for such porting. So that's why we have Mono for Blazor. As we discussed earlier, core CLR receives changes via the named pipes or COM interop. In case of Blazor Wasm, things get more complicated as we need also to have indirect access to the isolated browser environment and to the runtime, mono runtime itself. The runtime can be accessed using the JavaScript API from the JavaScript wrapper over the runtime itself called .NET.js, and communication with the page itself is performing through the WebSockets. Since each new page Blazor Wasm application creates a new separate runtime, just updating existing clients by adding new changes to them is not enough, because you also need to have a mechanism that aggregates and sends out the changes made before new pages was loaded, because they are not available in newly opened pages, of course. And by the way, updating, refreshing a page also causes the past runtime to stop and create a new runtime of the same page. So this is true. And also, but for example, if you navigate inside the Blazor app to the other component or page in your app, runtime persists the same, because you don't do a real navigation. You just do it inside the client side. So it's not a navigation, actually. So the runtime stays the same. In addition to changes to the source code that the standard hot reload mechanism in .NET covers, in the case of frontend in general and Blazor Wasm in particular, mechanism for updating static files such as JavaScript and CSS must also be provided. Currently, the hot reload infrastructure only supports updating the CSS files, including scoped CSS for specific Blazor Wasm components. The HTML code update logic must work both for specific elements with links to CSS files and for all available style tags in order for the update to occur correctly. Caching always creates new problems for developers, although it's considered a very useful approach in production. You have to use special tricks to ignore the cache when updating static files, the same CSS on an existing page. So let's summarize the Blazor Wasm specific items that should have been considered during the implementation. First of all, changes should be applied for both server and all connected clients. Different applying mechanism for different runtime types, because we have Core CLR, we have Mono. Delta aggregation and distribution is mandatory for both new clients and refreshing ones. So we need to keep all clients in sync with all changes, actually. Static files should be handled in completely different from .NET Core manner. And of course, HTTP caching should be bypassed, as we talked about that a second ago. Having dealt with the theory, let's move to practice. Let's analyze the implementation of hot reload infrastructure for Blazor Wasm in Rider. So it's worth stating with an overview of the architecture we have implemented. Some of the elements are covered by the fog of war, but it's worthwhile to understand what is going on so that we can go to each element separately in the future. I should note right away that there is no demonstration of hot reload on the scheme, a demonstration of the hot reload for ASP.NET Core server code. And here and below, as it has no differences from the usual Core CLR hot reload that we touched on in the first section. Here we have only client's hot reload mechanism. So Rider frontend in the core Rider is the core Rider process with the UI interface, where the user writes and interacts with the interface. Roslyn worker we are already familiar with, and here comes the browser refresh host. It's a special process that is responsible for communicating with the Blazor Wasm runtimes in the browser. One of the two key elements of this architecture of the hot reload infrastructure. Communication with it from Rider takes place via the RD protocol. It's internal Rider protocol that is used for almost all inter-process communication in the Rider ecosystem. Also worth mentioning is the browser refresh library at the right side. It's a library that is amped in the application server-side code in a special way, thus affecting the client infrastructure that is returned from the server using the HTTP. So now let's go directly to the sequence of generating and applying these changes. Firstly, Rider starts the browser refresh host that we talked before, WebSocket server that distributes changes across all connected clients. Then Rider starts the apps server with injected middleware through the browser refresh host, just browser refresh. When browser opens the apps page, HTTP request loads modified HTML with injected Blazor hot reload and ASP.NET Core browser refresh scripts. Then the scripts asks server for already applied changes from the past instances, applies them if needed. Then the script establishes the WebSocket connection to the browser refresh host. And when user changes source code, Rider asks Roslyn worker to calculate data. Yeah, so brace yourselves. There's more. Rider sends calculated data to the browser refresh host using the RT protocol. Then browser refresh hosts distributes the changes to all connected clients. Then ASP.NET Core browser refresh script applies new changes to the client, to each client actually, and also sends a post Blazor hot reload request to the browser refresh middleware to aggregate newly applied changes to the future clients. And that's actually it. It's a really high-level overview. It's okay that something could be unclear. It's okay at this stage. Client-side hot reload is finished at that moment, and after that, the user can observe the changed interface and behavior if no errors occurred at any stage of this process. And this is possible as the runtime may not be able to complete some specific changes that work well in core CLR, for example. Now let's look at each component separately to better understand how they work and why they are needed. Browser Fresh Host is a separate process that is a WebSocket server, actually. Also, in addition to WebSocket connections, it has a direct communication channel to the Rider frontend, from where it receives the request to apply changes. Its responsibilities include polling connected clients for available features, which may differ from version to version. So it's actually each running application through this Browser Fresh Host. They have a set of hot reload features, and they are incremented from each release from one release to another. And that's why we should also count this, keeping in mind that some clients can have different features, and they are not always have a one-to-one mapping from the SDK version to the runtime version. So also, one of the responsibilities is receiving the comments from the Rider frontend through the RD protocol and validating and actually relaying these comments to the connected clients, broadcast these comments to the connected clients via the WebSockets. We can say that Browser Fresh Host is kind of facet over the connected clients and a kind of hub for them. The clients in turn return almost no information except for possible diagnostics in case of change application error, for example. And you may wonder why it was necessary to create a separate .NET process to implement this functionality. Why not just to do it in Rider frontend? The point is that Browser Fresh Host reuses logic from a library called Browser Fresh Agent, which is a component or a part of open source .NET Watch application. Since the Rider frontend is written in the Java stack using Kotlin and Java, in order not to rewrite the whole thing from scratch, it was decided to put the logic in a separate process, which also simplifies support when updating the .NET SDK version. Also, this Browser Fresh Host actually lives no longer than the application, so we don't need to have it running all the time while Rider is running. So that's why it's simpler to just kill it, having the separate process with the implementation borrowed from the .NET Watch in some cases. Now let's move to the Browser Refresh library. This is also an almost unchanged version of the library that .NET Watch uses when calling .NET Watch Run, for example. It has several functions or responsibilities, all of which are implemented as native ASP.NET Core HTTP middleware. I would like to focus on how we add these changes to the user's application, because we host it together in the same application that user. We don't spawn anything else here, as this can be extremely useful outside of the hot reload context as well. We use two mechanisms to do this, startup hooks and host and startup assemblies. Startup hooks allow external code to run in the same domain as the main.NET Core application. This gives room for implementing different features, such as, for example, adding environment-specific security logic for loading assemblies. Imagine you have some production environment, you have deployed application, and you want to enforce some rules, for example, for loading assemblies. And you could do it via the startup hooks quite easily. Host and startup assemblies are similar to startup hooks, but they allow you to configure the application on the ASP.NET Core infrastructure level. For example, to configure the host builder. This is where the middleware we need is added, actually. What do these middlewares add? First of all, they provide additional endpoints for client code. Framework Blazor hot reload with post method submits applied changes from the client. get the same endpoint, but with get method, it returns all previously applied changes to on fresh client. So fresh client requests it, as you will see in future slides. Framework clear Wasm browser cache actually clears the local browser caches by responding to the user with the clear site data response header. Currently, it's used only for static files like CSS and nothing else. Also, the get ASP.NET Core Browser Refresh JS and Blazor Hot Reload JS, they respond with they just host additional static files that are used later in the client hot reload process. Let's focus on the client-side infrastructure now. Besides adding new endpoints, Browser Refresh library modifies the index.html file in a special way. It adds or injects the ASP.NET Core Browser Refresh JS script, which is the client part of the Browser Refresh host, to the end of the body tag, actually. By the way, because of the way this logic works in the .NET SDK, we've seen bug reports from users where this mechanism didn't work because they had response compression enabled. It's actually quite simple to enable and quite hard to diagnose, and which in turn removed the ability to edit the response clearly from you can't edit the response in as a clear text, just a text, because it is compressed. And because our startup hook and starting hosting assemblies are added below the actual user's code, we can't just to inject the stuff before the compression. That's actually the problem. Also, compression at the level of hashing, additional hashing, and even if we could modify this text, we will fail the hash checks. So that's also we need to keep in mind in implementation, implementing this stuff. But there's nothing actually we can do with that right now, because the .NET team has some plans of changing this behavior, but not for now, actually. Let's move now directly to the scripts that work with runtime and accept changes from browser refresh host. Let's start with the ASP.NET Core one. It set up the connection to the browser refresh host WebSocket server and handles messages from it, applies changes on request, provides server with support and hot reload capabilities, some sort of versioning, yeah, and shows nice check mark at the end. What is Blazor hot reload actually? It's a special additional quite tiny script that is used only to fetch the changes that we applied previously on previous instances, previous pages, and it is loaded by the Blazor WebAssembly script on startup. Actually, that's a little bit of typo here. It is loaded not by the script, but by the .NET interop, as we will see in further slides, and also applies this delta previously aggregated on the server. Finally, let's go to the code. The logic in the script will execute as soon as the script is loaded. So in this script and the further down the slides, the code is a bit simplified and cleaned up from additional checks, validations, and so on. The full code can be found on the .NET Watch source code, links at the end of the presentation. Near the number 1, the variables where the real WebSocket endpoint and the server K will go are highlighted in green. So they will be replaced by the string manipulation on the response side. So they are delivered to the user client side with the actual strings here, because after a browser refresh host starts, it hosts occupies some ports for the WebSocket and generate the key that is after that used by this infrastructure. How it's passed actually. When we start browser refresh host, we gather the information about port and key. And then when we start actual application, we provide some additional environment variables that are read from this actually from browser refresh middleware. And then they are used. So this is done by environment variables actually. And the most interesting comments that come with the browser refresh host are highlighted near the number 2. The full list may vary from version to version, but we will focus on these two, actually. And let's go directly to the application of changes to static CSS files. First of all, we reset the browser cache, solving the problem of future loading of old styles, because without that, we may load old styles even with the other mechanisms applied for clearing the caches. Next, near number 2, the most interesting part starts. To reset an old style, we create a copy of the style tag, then changes the reference, the link in it, so that it contains the current timestamp, which ensures that the browser will make a new request to fresh CSS file. That trick is used in a lot of different hot reload mechanisms across the web frontend, for example, in React or something like that. Once the new file is downloaded, the old style tag is replaced with the new one, and the old one is deleted. So actually, we fully replace the script tag, and this also forces browser to refresh styles in different elements. That's the kind of uncomplicated magic that goes into updating these CSS static files. Then let's move on to applying .NET changes. It's pretty straightforward here on this stage, because JS client-side forms applying consists of 2 parts. First, we call .NET apply changes via the JS to .NET interop. Then we notify the server that the changes have been applied on the current client, and this is to ensure that future clients also get the changes on their startup. Now, a tiny script. This is the whole content of it, actually. The second script is just to get the actual applied hot reload changes from the server at the start of a new instance of the Blazor application. That's what we put them in there in the previous slide. Then we go back to the .NET from JS again by calling the same apply hot reload as we had actually here on the first highlighted line. That's actually it. And then let's look at how this .NET client-side interop looks from the .NET side. We've seen how it's called, but how it's actually look. In the Blazor core source code base, there's a special WebAssembly hot reload class that configures the interop and is essentially a layer between the JS code and the Mono runtime. Near number 1, you can see the call to apply old changes from previous clients. Near number 2, you can see the import of JS function actually to do that. Then in number 3, you can see the methods that we export and use on previous slides. It in turn calls the hot reload agent apply changes method, and the hot reload agent code it's also bundled with the SDK. Actually, it's quite complex, but it boils down to calling the metadata updater apply update, a method from the system reflection metadata namespace. Internally, this method, depending on the implementation of the runtime, applies the changes already at the level, at the really low level for each runtime. For example, in Mono one or Support CLR one, this is where implementation differs. The mechanism for storing changes for future runtimes is quite simple. After notifying the server of the applied change, it stores them in a thread-safe collection in a strictly ordered manner. These changes are similar to Git commits in concept, so they need to be applied in the correct order, because next changes could depend on previous changes. That's quite often, for example, when you change UI consequently and you have one change of the button, for example, another button, and they need to be one after another. Then when a new runtime is started, the changes collected on the server will be returned as a response and immediately applied. Theoretically, if the hot reload session is long enough,
launching a new runtime after many iterations and a lot of different instances can be much slower because of the N1+ problem. We have a lot of changes to apply. They are not aggregated in terms of, they are not collapsed into one single change. They're just stored as a couple of changes, as a set of changes. And however, in practice, hot reload sessions are really rarely long because it's actually, and changes are quite small. So each application of the change is quite easy operation to perform. Knowing what we know now, let's trace the journey of change from the beginning to the final recipients. First of all, Wasm calculates changes on request from the IDE. Then changes are applied to the ASP.NET Core server level. That's what is out of scope of this talk, but it is actually done prior to making them on the client side, because we, for example, need to provide newer style CSS files, newer other stuff. So we need just to do it before. Then actually IDE sends changes to the browser refresh host via the RD protocol. Browser refresh host after that broadcasts the changes to each connected client page with the ASP.NET Core browser refresh script using the WebSockets. And ASP.NET Core browser refresh calls the managed wrapper apply hot reload delta using the JS to .NET interop. Apply hot reload calls the actually metadata updater apply update and passes changes there. So that's what we saw right before. And after successful apply, ASP.NET Core browser refresh sends the changes to the ASP.NET Core server for future clients. Now finally, let's summarize the entire thing, what we talked today. Hot reload is really crucial for the UI development, as it's really speeds up the development and simplifies the feedback loop for doing such small and consequent changes. Blazor Wasm hot reload consists of two stages: server hot reload and client hot reload. So, and we need to apply on both of them, and that's also need to consider the way of rolling back the changes when, for example, something went wrong, but unfortunately there is no rolling back mechanism. So we need to just ask user to restart, for example, the application in case CoreCLR successfully applied the changes, but Mono didn't. Runtimes on new and refreshed pages will receive changes from previous pages runtimes. This is really important, and that's why I am repeating this again and again for the whole the presentation, because it needs to be persisted in such a way that future clients should receive also the changes that we done to have a consistent application state. Then static files are made differently from regular .NET Core updates, because we need to do it in completely separate hot reload, but this is done entirely on the JS side. Server-side hot reload infrastructure is injected into app server using startup hooks and hosting startup assemblies technique. So this is about modifying the client-side scripts and so on. And the client-side hot reload infrastructure is injected directly into index.html and represented in several JS files with interop calls to .NET side. That's there are a lot of interop coming from firstly from .NET to JS, then again to .NET. So there are a lot of layers of reality coming here. So it's sometimes hard to debug and to traverse, but that's quite interesting. And messaging and delta applying between IDE and Blazor client is done indirectly using WebSockets and RD protocol through the Blazor browser refresh host, actually. And that's pretty much it. I hope that the talk was not only brain-bowling, but an interesting deep dive into the magical functionality of Blazor Wasm. And thanks you for your attention.
You can find the slides and links from today's talks by following this the link or from using the QR code here.
Hi, Andrii. That was a fantastic session. Thank you very much for that. I had no idea quite how many moving parts there were to this.
Yeah,
it's quite a complicated scenario.
Yes, that's it, because it has a lot of actors acting in this scene. So yeah, it's quite tough, and it's not straightforward to see the why it's so a lot of things going together.
Yeah, just call it the Atom Smasher, because it feels like that. There is a lot to it. So there was a lot of questions too. Well, I'll start. So somebody toward the end mentioned in the larger projects, hot reload isn't working for them. Is it just that you can make some minor changes, and I'll add this on top for myself. How far can I abuse this? Like, if I make a change, run it, can I then write like half the app while it's running? Because I'm going to try to pull that kind of crap. So can I?
Yeah, actually, according to the large projects, we have some reports and limitations and problems with that, because when in theory it comes quite easy. You modify one assembly, you modify one static file, and everything goes quite well. But when it comes to real application, when it comes to different proxies applied, when it comes to different assemblies amped in the for example, if you have Razor components libraries, or when you have some different injections of complex things in real applications, of course, hot reload could hang up and doesn't work as it intended to work. But in such cases, each case is quite unique, and we need to test it and reproduce to actually have it properly made. It work with our infrastructure. We are quite limited in things that we can do, because the half of all this stuff is done not only on our side but on the runtime side. And if runtime has limitation on that a particular thing, and that means that we can't actually do it properly. And to test it, actually, that is a problem with runtime. It's always an option to run the app through the .NET Watch Run, and to see if it works there. If it works there, actually we can support it also. But if not, it's nearly impossible from our side to have it done without having the pull request merged into the .NET runtime.
Wow, and that raises an interesting question as well. How do you test this? I know Rider and Sharp, we've got thousands and thousands of automated tests, but there are so many moving parts here, so many pieces. How do you, have you got an infrastructure to kind of spin up everything and make it to test it?
Actually, we use we are on the way of writing the proper test, because previously a couple of years it was small amount of tests for Blazor itself and for the debugger and hot reload, and hot reload landed into Rider just in the beginning of this year. So it's a bit a new feature, but we are on the way of writing proper tests for that. How it will be done actually is that we will have a complete integration tests. So we will launch the Rider in the headless mode. We will launch the Chromium browser also in headless mode, like we had in the debugger tests, for example. And all this infrastructure we will have up and running, that the whole thing that we have here, almost without any mocks and stubs, and it will just work. Of course, it will also introduce some flagness and all the stuff, but we'll, I think, manage it out.
Mm-hmm. Yeah, I know our QA department are very busy with all of these things and doing lots of good things with the testing there. But yeah, automated testing would be fantastic. Although I can imagine, yeah, flaky tests this one could be a bit tricky to get right there. Another sort of question, really, you kind of mentioned, hot reload has only really come in with this year. Right at the start of your presentation, you were saying that there's lots of different implementations of hot reload. I kind of really never thought of it like that, but it makes sense. You got mono, you got core CLI, you got all this kind of thing. Do we have are the processes for hot reload common and shared, or are we actually having to do custom support for every single different type of hot reload, and therefore it takes time?
Yeah, actually, if it comes to, for example, regular hot reload, that is when we hot reload, for example, changes in core cellular runtime or in mono runtime, the mechanism of applying the changes inside the app domain. So when we have changes somehow made their way to the runtime, and the application from the code perspective is similar. So we just call metadata updater from the system reflection metadata package, and that's it. But the difference is in the transporting the changes from the IDE to the runtime mostly, and also XAML hot reload, for example, works in an absolutely different way. They inject some different stuff in the app startup, and they do completely different work on that. But the core cellular hot reload and Blazor Wasm hot reload, mono hot reload in this case, are quite similar on applying changes, but are completely different on transporting the changes from the IDE. So some things, I would say, some things that could be shared, but a lot of changes, a lot of differences we can't share. We need to implement it again and again. From the rider perspective, for example, when user changes something and then see that the bar that apply changes and so on, this is actually quite similar to all different code reloads we have. So from this side, we only the one missing part we didn't implement yet is that when you, for example, when I showed on the slide, when we have supporting root changes, it is not supported in Razor files right now, but it is supported in C# files, and we will also support it in the future.
So is that a limitation? If it's not supported in Razor, is that a limitation from the Rider implementation side, or from the .NET runtime side?
This is the limitation of Rider. So we just didn't implement that, but we will do in the future. Yeah.
It is hard to know. I mean, from your talk as well, it's a little hard to know quite what is Rider's responsibility and what is the runtime's responsibility. So I don't know, how much have we built? Well, not me, not we. Yes, I mean, look, I'm taking credit for this. How much have you built versus how much is being provided by the runtime?
Yeah, I would say it's 50-50. So we have from like as you said, we have like hot reload have two parts from this perspective: the runtime side and the tooling side. And the tooling side should be almost entirely implemented by us, but we also reuse the logic from .NET Watch because we don't want to implement it on our own, because when changes come into the .NET Watch, we also need to port them to our own implementation. Of course, if it's in a different language, it's really hard to do. So it need to be done manually, and but we are trying to base our changes on really already made changes in .NET Watch. So I would say 50-50, yeah.
That's crazy. Again, I had no idea of all the moving parts that were associated with this and how much effort has to go in to get it supported, and that each different type of hot reload has to be implemented separately and stuff. It's crazy things.
Let's add more to it. Because why not? So Rider has remote development. Does the model change for this? Does it get worse? Do you need to adjust infrastructure? Does SSH tunneling take care of this, or no? How does that work?
Wow, that's great that you mentioned remote development, because that's the feature that I'm working on right now on the actually for Blazor. Actually, it has a lot. It adds additional layer of complexity because you have have done all this port forwarding, a lot of stuff additionally to work this out. But I'm planning to add this to work like that. So we will have only browser running on the client, and all other stuff, including all other infrastructure that I mentioned today, will be on the backend. And this adds the complexity of having the forwarding of WebSockets, forwarding the other stuff. But actually, it will work like that because, for example, there is also a debugging that is was out of scope of this talk, but also there is some difficulties when you have to apply the changes and changing the symbols and all the stuff in the debugger side. And but that it will work like that, I believe. So only the browser will be running on the client, and all other stuff will be done on the backend.
Yes, so, I mean, just to back up a little bit in case people aren't aware of what the remote development is there, that the whole idea of that is running Rider with your source code and all the toolchain and everything on a remote host, and then you connect to it from a local machine, and your local machine has a essentially a cut down version of the IDE of Rider itself without any kind of language processing going on there. It doesn't download any files or anything, or everything runs on the remote host, and you can connect to it and get the same sort of experience. And so what you're saying here is then in this scenario, the ASP.NET server would run on the remote host, the browser stuff runs locally. And does that mean it brings down the WASM stuff as well locally? So all of your WebAssembly runtime runs locally?
Yes, that's right. Because they are running in the under the browser pages, and if browser running on the client, the runtime also will run on the client. But of course, we need to have a communication from the backend to the client, to have all this working stuff like breakpoints and other communication with the debugging side, applying changes. All this will be done via the port forwarding and other techniques. But you're absolutely right with this.
Yeah, that does add an extra layer of complexity to everything.
Yes.
Yeah. Well done for suggesting that one, Rachel. Yeah, just to try and make it even more complicated.
I actually now forget how many layers there are. There's so many.
Yeah.
All right. How about a softer one? Also, it could be a bit of an interview question. What feature are you still working on that you think will have a big improvement? It's from the chat.
So as I mentioned, the remote development for Blazor, this is my first priority for the Blazor subsystem, actually. And what I'm working also in the future, we have some gaps, for example, to the debugging support. Right now, for example, we have the best debugging support for Blazor across all IDEs and editors, because we implemented in new debugger implementation from this year has another a layer of complexity and implementation that currently in the other IDEs and editors. And but it still lacks some features like Smart Step Into for the Blazor files. Some other things related to Razor.
Is that debugging Razor files? Is that debugging?
Yes. So Smart Step Into, Smart Step Into inside the Razor files, Razor component files, because Smart Step Into works perfectly in Blazor for C# files, but unfortunately it's still unsupported in the Razor files. That's pretty much it for the plans, from Near's plans to accomplish.
Yeah, sounds great. Good luck with those. That's tricky.
Thank you.
I think we've got another couple of questions from the chat as well. I think it was going back to sort of some of the diagrams you were showing there. Does Rider deliver the hot reload deltas to all of the connected clients?
Yes.
So if you've got a browser, so if you've got multiple browsers, multiple tabs, multiple iframes, and they're each running a runtime instance, if you hit something in Rider, it pushes out to everybody.
Yes, that's right. Okay. Can you show my slides again? I will just I will show this specific
Yeah, I'll do that just now. Hang on a sec. There we go.
Let me show the actual architecture stuff here. Yeah, so as you can see here, we have a browser refresh host, and this is the entry point for changes coming from the IDE, and then each page, regardless of the browser when it's open, it connects to this browser refresh host via this special injected JS script, and then it become acknowledged by the browser refresh host, and after the change coming here, it broadcasts to the all connected clients. So more on that. When new page is opened in the browser after some changes were applied in the previous client, this new client will also receive these changes as I showed here. So each change is tracked on the server side, and when new page is opened, it also borrows all these changes came from the previous runs or previous pages. So that's it, yeah.
Yeah, so the broadcast, so the I've forgotten, the browser host, that basically tells the clients to get the deltas from the server. So it doesn't, the browser host doesn't, let me rephrase that. Does the browser host push the deltas itself, or does it tell the clients to go get the deltas?
If it's a change that that is happening right now, it goes through the let me show you, from the browser refresh host by itself from the rider, but the change that is aggregated on the server for the further clients, it's coming from the client side. So when client applies changes on, let me show the code. When client applies changes here, as you can see, after that we push these changes to the server using the Blazor hot reload endpoint, and that means that further clients will download these changes and apply them by this logic done in Blazor hot reload. So it downloads and then apply one by one coming from the server. Yeah, but browser refresh host doesn't send changes to the server. It is done by the client because these changes should be preserved only after client fully acknowledge that and apply them. That's why we can't just throw it to the server from the browser refresh host. Yeah.
Yeah, that makes sense. Thank you. Thanks for going over that one. Rachel, have you got a question ready?
Yeah. How about if this is another one of those interview kind of questions? Shall we hire Andrii? Let's see. If you were to design hot reload in .NET from scratch, what would this look like? Would it look the same, even close to the same? Would it need the same infrastructure? What do you see that's right off the top that might be more efficient?
Yeah, so if you're talking about making this whole stuff from scratch, that's a tough one. It's like the .NET team had a perfect job of perfect work on this stuff, and they implemented it's quite great. And what can be done better? I think that some tiny parts of this whole mechanism, for example, the let's say the injection, the injection of actually. Let me jump. Yeah. So, for example, injection of this script could be done better. And for example, it's because it adds the problem of having the response compression, as I mentioned. So, and this is done very rough. So this script is added just by the string replacement of the body tag. So they just find the closing body tag and then just replace them with this script, and it could be done better. But it is nothing related to performance. Maybe also it is a great idea to aggregate all these changes in some snapshots or something like that, to apply them not one by one for further clients, but as one major change. It's of course creates some problems. For example, when different clients have different set of changes applied already, and we need to somehow find the difference and apply only the part of the change that needed, but that could improve the performance, I believe. So it will look like a real event sourcing mechanism here. So it's really similar to event sourcing. So some mechanism that involve event sourcing, they also have the snapshots and some sort of aggregated data stored in one event, for example, and so on. So yeah.
Very cool. That's a great question as well. But it's from the way you've described everything, it kind of feels like this has to be the solution mostly. You know, it's like you've got these problems.
And one thing I also want to mention in terms of what could be done better is the diagnostics, because when it comes to applying changes, runtime is very silent if something went wrong. And that's a problem because debugging the Wasm runtime itself, not the code, but the runtime itself, it's quite a complex task. And because it includes not only JS side debugging, but unmanaged debugging inside the browser. So it's quite tough. And it's the Microsoft, the .NET team actually that works on that. They have a great article of how doing this debugging. It's hidden in somewhere in the sources of the .NET runtime, but actually it helps with that. But it's really great to maybe see in future to have better diagnostics, and that's what I would done better maybe if I would implement that from scratch. That's diagnostics are very important in finding why the changes were not applied. For example, what specific thing was wrong on apply. So we have great diagnostics from the Roslyn. Why we can so as I presented one of the slides. So the diagnostics coming from Roslyn on before applying, they are great actually, but this is not. They are validated on the delta calculation. This is not diagnostics on apply. So and on apply, some things went wrong. So that's why better diagnostics is a key for better hot reload.
Yeah, speaking of the unsupported changes, I like the phrase rude changes. Speaking of the rude changes, is the list of what is and is not supported changing as the runtime, with different versions? So are we going to get to the point where we can replace more and more types of code?
Yes, I think so, because the .NET team, from one version to another, they improved the hot reload mechanism, especially for Blazor, for example, because, as I said, the Blazor is another type of runtime, and that's why the features should be implemented twice, one time for core seller and second time for mono runtime. That's actually true for any feature of the runtime supports, and not only the hot reload. But they doing great of reducing the number of unsupported changes. But some changes, I believe, maybe will never be handled because they involve really a lot of runtime modification from things like I don't know. I don't have an example, but I think that some things that will never be handled correctly. But majority of them will be, I believe, done in the future. If there will be like a request from users on that, because so I believe that they will implement.
Yeah, because that kind of plays into another question we had from the chat, which was asking if hot reload will ever be as efficient as other stacks like JS and PHP, because it can, it can be really frustrating when it comes to the stack because you lose time rebuilding the solution. So I guess the more things that can be supported here, the better that would be, I guess.
I think that it depends on the specific features that the user means, because I really also think that in web front-end frameworks, the hot reload works better. It is simpler to implement in web frameworks because in majority of cases,
Of course, we have TypeScript that we need to preprocess, but actually, the idea of JavaScript is dynamic stuff, and in .NET we have complex runtime side of the question and the compilation side of the question. And so, of course, somewhere in the future it will be as efficient, I believe, as the front-end one, but not now. I really think that it's a great technique, but it still lacks some features that will make it feature parity with the other frameworks like React or Angular or something like that. So yeah, that's it.
Cool. And just to follow on as well, what you're saying with the unsupported changes, you're having to do it twice, once for core CLR, once for mono. Do you know if there's a timeline for replacing mono with core CLR in WebAssembly?
Unfortunately, I don't know.
Is that going to make your life easier or harder?
It will make my life harder because I need to re-implement all this stuff. Even with the shared code, it will still have a lot of things done. By the way, I don't know what is the state of WebAssembly threads in the .NET 9, but right now debugging with it doesn't work in any of IDEs and editors. I don't know what's going on, but yeah, we will investigate in the future. But actually, that's about the things that will make my life harder because thread support. Right now, debugging Blazor Wasm apps, it's just debugging one thread, managed thread. Mm-hmm. And in future, it will have a lot of threads, and that maybe will have another thing to accomplish.
Well, it seems that you like complexity, so this is
yes.
good. We have faith that you can make it work.
Yeah, that's true.
Rachel, do you have any other questions?
Yeah, there's one more here. From the chat, someone asked if there's any capabilities for Blazor Wasm, the app itself, to acknowledge that the hot reload happened. And I will ask, because of that question, looking back yesterday at Konstantin's talk, he explored, elegant and crazy, and also the question I posed before about abusing things. So is there a capability for the app itself to acknowledge this? And then can we abuse that and patch apps on the fly?
Yeah, so that's a great question, actually. I don't know. I don't know at the moment. So I didn't think about that in that manner, about having the client side know about the hot reload happened. Because we, as for example, in the debugger, we have such event. We can actually react on the event from the mono runtime about the edit and continue happened. But actually on client side, there is no such API, I believe.
So a nice try at being evil there, Rachel, but you've been foiled this time.
At least 50% of my attempts get through.
That's still a very high percentage. I think that might be all the questions we've got there. I think
bonus
is that right,
is tied to that, right?
Sorry.
Bonus is tied to that percentage, right? Or do I have the wrong metric?
The evil percentage, yeah. Yeah. Well, mine's on bringing that down. Yours is raising it up. So we've got some tension here. Anyway, yeah, I think that's all the questions we've got. Andrii, that was a fantastic session.
Yeah.
Really interesting deep dive into all these moving parts, all of these spinning plates that you keep going. I'm amazed really at how complicated it is and how well it can work with all those different moving parts. So once again, thank you very much for that.
Thank you very much, folks.